Today is the third day of our lecture on classical mechanics. In the first day, we discussed about the Lagrangian mechanics. Then we talked about the Hamiltonian mechanics, their advantages, disadvantages. We also took some examples and solved them. How we get the equation of motion using Euler-Lagrange's equation as well as from the Hamilton's equations of motion. On the third day, the topic that we will be talking about is central force. You might all be aware about the central force. So what I have decided is today I will be starting with the definition, its properties, and the force, effective potential, and the theory of the bound orbits, unbound orbits, circular orbits, and so on. Let me start with screen sharing. So first, the definition. What do you understand by a central force? Central force is basically a force which is along a line that is connecting the origin as well as on the body on which the force is being applied. Or in a proper definition, it's a force which is directed in such a way that either it is away, that is, it can be attractive or repulsive from a fixed center, force center that we talk about, and its magnitude depends only on the distance from the center. For example, I'm saying this is the origin of the force, and this force will be either away or towards. That is either repulsive or attractive in nature. For example, next thing is it will depend upon the distance between the center of force as well as the mass or the particle on which it is acting. That is distance. For example, if this is mass m1 and this is mass m2, this is mass m1, m2, and if the distance is same, then the force will be same. Force that is acting on these two bodies, it will be same. So F is equals to central force. F is equals to, depending upon the magnitude of the force, which is depending upon the distance or the line connecting the center of the force and the mass, r cap. It can be attractive and repulsive depending upon what is the value of Fr. If Fr is negative, then the force will be attractive. If your Fr is positive, then the force will be repulsive. And next property, it is always conservative. Conservative means I can express my force in terms of grad V. This is how is grad V. Or you can say conservative force. What do you understand by the conservative force? That is curl of F. Curl of that force is equals to 0. In mathematical term, you can say. Okay, these are some definitions and the properties we can look at. Now coming to the examples part, we are all aware that one of the most common example is the gravitational force. It is a central force. However, this force is not depending on one body. It is a two-body force. Both bodies apply force on each other, but it is directed always along that line which is connecting two bodies. Similarly, we have the electrostatic force in that we have Coulomb force. Same thing, two-body force. You can see if this is Q1, Q2, the force will be along this line. Depending upon what is the charge, either it is both are positive or one is positive, other is negative. Depending upon it will be repulsive or attractive. So the forces that we have discussed, they are two body forces. Okay. uh, any other example? Okay, we have spring force also. that is also a that is also a central force. Now in nature there are many more problems where we can find that we have a central force. Now moving on, we know that the central force will only depend upon the distance. Okay, its magnitude, it will only depend, it is our dependence only, it is conservative in nature. And the third part is, in central force case, angular momentum is always conserved. Angular momentum is conserved. That is L. If I'm, this is not Lagrangian, okay? Don't get confused with the Lagrangian. Let me make this a simple L. L equals to constant of motion. That is, your angular momentum will be conserved. How do you represent your angular momentum? Angular momentum is R cross P. So you can derive this also. This is a very simple derivation. How your angular momentum is conserved in case of a central force. Second thing is central, we will do this derivation. Don't worry, let me just point out few things. Then the central force motion. First, we know that L is constant. It is kind of constant of motion. Second thing is, your central force motion is always in a plane. It is a planar motion. That also, when your L is constant, the motion is always in a plane. Let's just start with how you can find out that L is constant. You can simply take as L as equals to R cross P, where R represents the radial distance, P represents the linear momentum, and just find out dl by dt, which is dl by dt is what? It is your torque. dl by dt is torque. Find out dl by dt. If the external torque is 0, then your L comes out to be constant of motion. So dl by dt, you can open this R cross P, dr by dt cross P plus R cross dp by dt. Your dr by dt is nothing but the velocity, radial velocity. Then P plus R cross dp by dt is your force. We also know that V cross P, P is your mv. So your V cross P, it automatically comes out to be 0. You're left with R cross F. However, we know that here we are taking what kind of a force? This is a central force. So we know from definition, central force depends upon F, and it is always along the radial distance. So this second part also comes out to be 0, and you get a quantity that del dl by dt is your 0, which means that L is constant of motion, proving that your angular momentum is conserved. Okay, both in direction and magnitude. This was your first point. Now the second point is, central force motion is always in a plane. Now, how can you say that your central force motion is always in a plane? For example, I'm talking about the elliptical orbit here, and this is your R. This is your R, your velocity will be V, this will be your R. And your L is constant, correct? Your L is constant. L is your R cross P, or I can write this as L as equals to M R cross V. mr cross v, P as mv. So r cross v, as you can see from this figure, I have taken an example, that is the gravitation one, elliptical orbit. This is your r and this is your v. It is only possible when the motion is, L can only be constant when your motion is planar. Both lie in the same plane. Okay, so this was about the properties, that is your angular momentum is conserved, the motion is planar. We can also look at one more example. Here we talked about L as constant. What if your L is 0? Can anybody give me example where my L is 0? Any example of this? Particle in a straight line? No. For a center of motion. That is particle in 1D, right? Performing to and fro motion. Yes, exactly. So here there is a particle which is performing a to and fro motion. So your R is also this. R is also this. Then your V is also this, same direction. So what comes out to be? L comes out to be 0. Okay. Now moving on. Okay. Now what we will look at after knowing all the properties of a central force, we will look at how do we represent the Lagrangian for a central force. Okay. Now what we will be doing, we will be extracting the concept of the cyclic coordinates here. Yesterday in the previous class, I talked about cyclic coordinates or the ignorable coordinates. Okay, so let me just first write down the Lagrangian of a central force. So the Lagrangian for a central force will be T minus V, where the kinetic energy is given by half m r dot square plus r square theta dot square. Okay, I'm writing this in polar coordinates. R dot square minus VR. It's a potential which is only depending upon R, radial potential. Okay, not depending on theta, because we are talking about a central force here. So this is my Lagrangian for a central force. Now we can see your generalized coordinate R is present. Your generalized coordinate theta, however, is absent from the Lagrangian of a central force. What does this tell you? This points out that your theta is a cyclic coordinate, and its corresponding and its conjugate momenta, that is your p theta, which is nothing but your angular momentum, will be constant of motion. This we have already proven. Here, this we have already proven. So this information we are getting from the Lagrangian of the system, Lagrangian of the central force problem. Okay, same thing. This is the beauty of identifying cyclic coordinate. This is one of the, you can say, the properties of the cyclic coordinate. This kind of information can you can automatically get if there is a cyclic coordinate. Okay. Now, generalized coordinates. How many generalized coordinate a central force problem is having here? It is your R and theta. So they will have the corresponding conjugate momenta also, that is PR and your P theta. P theta is your angular momentum. Same thing. Okay, that I was talking earlier. Your P theta is what? We know how to find out the conjugate momenta, which is your del L by del theta dot. This is the angular conjugate momenta for the generalized coordinate theta. Then similarly, del L by del R dot, this will be the conjugate momenta for the generalized coordinate R. Okay, so what we will be doing usually in this cases, we take this value as L and then equals to mr squared theta dot, and we write this in terms of this. Okay, theta dot is equals to mr square by L. This we will be frequently using, but not right now, but this is most important part here. Here, this quantity, as you can see, since your angular momentum is it is a constant of motion, this is constant. Okay.
Yes, sir.
Now, I will not go into detail. We will not be discussing about the Kepler's law here. What I want to do is, I want to straight away go to, if I know my Lagrangian, I want to know what is my force. How do I represent force in terms of the generalized coordinate, and how I will be writing my potential. Okay, so from the Lagrangian itself, I can find out the force. This is the equation for the force, mr dot dot minus mr theta dot. All I have done is I have plugged in the Euler-Lagrange's equation here, okay, and found out the value for Fr. That is your force. Again, rearranging this, what do I get? This is MA simply. So external force. However, this term, that is your minus L square by mr square. This is also present in my force term, central force term here, Fr. Okay, this will be contributing. This will be affecting also. We will see earlier. We will be taking few examples how to plot this force by for example, inverse law force, or Hooke's law force, whatever we take there. So we are getting two terms, and this minus L square by mr cube, this is also contributing, not an actual force, but it is present there. Okay, now since your Fr is written as, or you can say your equivalent or effective, basically, let me use the term effective force, which is your Fr. We know whatever force you're taking, either inverse square force, whatever force you're taking, and then we have a term L square by of mr cube. L square by mr cube. This is the additional term. Similarly, if I want to write my effective potential will now be the potential. If I'm talking about inverse square law force, for example, Fr equals to K by R square. Okay, then my potential will be, this potential will be minus K by R. Okay, so some constant I'm talking about, minus K by R. You take this. Yes, hello.
The effective potential will be with L square upon 2 mr square, right?
Sorry, no, this I have not written the whole term. You have to write this term also.
Okay.
Hello.
Yes, ma'am. Yes, ma'am.
Okay, this is not the whole term. I'm just talking about, if I'm taking this inverse square law force, then its corresponding potential will be this. However, the effective potential will be plus L square by of
2 mr square.
mr square. Correct.
2 mr square.
Yes. Okay, 2 mR square. Yes, yes. Because this is the minus grad V only. You have to take F.
Yes.
Effective will be grad V. Okay.
Yes.
This is your effective force. Now this is your effective potential. This is important because whenever you take any potential, this is how you will be plotting it. It is not just that particular potential we have to do. This term will also contribute in the potential part, here in the force part. For example, we can start with, okay, this example I have taken, inverse square law of force. How will you plot the potential part? Let me just plot the effective potential for a inverse square law. That is your VR equals to minus KR. Okay, if this is your R, this is your V effective. This is your V effective. Remember, this is your V effective. Okay, this is looking very cramped, right? Let me go to another slide where I have space. Yes. This is V effective. This is your R. We know that V effective is equals to VR plus L square by 2mR square. Okay. So here your VR is nothing but minus K by R because I'm taking inverse square law force. Okay. So as you can see, look at the slope. This is 1 by R square. If I will plot this term, okay, so it will be, this is your L square by 2mR square. Now I will be plotting minus K by R. This is a attractive potential. So its slope will be okay. There's a difference. This is more steeper than this.
Yes.
Now, what will be the effective one? What do we see here is for the lower values of R, for the lower values of R's, this term will be dominating. However, for the higher values of R, this term will be dominating. Okay, so let me take this. Okay, this is your resultant potential. Clear?
Yes.
Okay. Now, what we will do is, this is the most common example that we will be taking. Now, we will consider different approaches. Different approaches in the term. We will be taking for energy E1, say when energy E1 is greater than 0, this kind of energy you can say, or then you can say for this one, E2 equals to 0. You can take then here, right? Let me write this here, E3. E3 is less than 0, and then the minimum one, E4. Let's just try to draw the orbits. Okay. For E1, coming to the first part, do I have space needed? Now for E1, that is your, which is greater than 0, what do I see? I will be having, I'm so sorry, let me just use another slide. square. First, E1 greater than 0. Here, this for E1, it is energy is greater than 0. What do you see is how you will be drawing this potential? It will be kind of this particle coming from an infinity. It will, okay, it doesn't look good here. This is for E1. This is E2 equals to 0, E1 greater than 0. Then E3, E4. Okay, we will be looking at the turning points here. For E1 greater than 0, the turning point is this, or you can say the intersection point. A turning point is basically where your radial velocity it is equals to 0. So this is a turning point. Let me just take this point as R1. This is your R1. Okay, so this is for E1 greater than 0. I'm drawing an orbit. It comes from the infinity, and this is the closest approach. This is equals to R1. Then it turns around. This is a turning point. It turns and then goes back. This is the trajectory it follows. Okay, as you can see, this is a kind of an unbound orbit. Unbound orbit. This, you are all familiar with this kind of trajectory. This is for the when scattering takes place. When scattering takes place. Okay, this is when the scattering takes place. Now moving to the second energy, that is E2 is equals to 0. E2 is equals to 0. We can take one more example. One more thing is, I'm not going into deep what your eccentricity is, but let's just write down your eccentricity as equals to under root of 1 plus it is actually square by mk square, if I'm not wrong. Is this correct? Whatever I'm writing, is this correct? I think. By 2 mk square, yes. Okay, this is your eccentricity. As you can see, for the first part, when E1 is greater than 0, how will you find out the trajectory? From this value, you plug in the values, it will be positive. So your eccentricity will be greater than 1. Correct? Which automatically gives you what? When your eccentricity is greater than 1, it gives you what? Hyperbola. Hyperbola, yes. Okay, this is your hyperbola. Now going to the second part, that is your E2 is equals to 0. When your E2 is equals to 0. So when you plug in, insert the value of E here, this is 0. Then your eccentricity is what? It is your 1. What kind of trajectory you will be getting? A parabola. Correct? For example, this is hyperbola, then you will be getting a parabola. So what I can do is, the turning point here is this, you can take as R2. You can take as R2. So this is your R2. Now moving further, for E3. For E3, intersection points are there are two intersection points, you can say. Let me take this as R3 and take this as R4. Okay, two intersection point, and the energy is less than 0. When you insert the value, energy value here, as you can see, if I will plug in the value of energy as less than 0, I will be getting eccentricity as
Between 0 and 1.
eccentricity less. Hello.
Yes, yes, sir. Yes, eccentricity will be in between 0 and 1.
Okay, 0 and 1. Okay. I'm not taking eccentricity. It is less than 1. It can be ellipse or it can be this is not, when it is eccentricity is 0, then it is circular orbit. Okay. Yes.
This it's an ellipse.
This is an ellipse. Correct. And the motion is bound, as you can see. For the second part also, that is E2 is equals to 0. The trajectory was a parabola and motion was still unbound. However, for the third case, when energy is less than 0, the trajectory or path it follows, that is your elliptical path. Okay, and the motion is bound. Motion is bound. Elliptical path and the motion is bound. Okay, so this is your R3, this will be your R4. Elliptical bound motion. Now for the fourth part, that is E4. Your E4 is what? This is your minimum point, as you can see here. E4 is less than E3. It is less than E3 and less than 0, as you can see here. So for E4, you can find out del V effective, that is your minimum. Del V effective by del R. Okay, del V effective by del R, minimum point. How do you find out the minimum? You have a function, you find out its first derivative, equate it equals to 0, and then second derivative, if it is less than 1, then that is your minimum point. You can find out. Okay, for this, you will be getting a bound orbit and the trajectory will be circular. The trajectory will be circular. Okay, now this was about, okay, this we plotted for the inverse square law force. Similarly, you can do for, let me talk about spring force. Okay, everybody do for the spring force. Spring force के लिए करो तो try करो please everybody. Where your potential is given by half k r square. First plot the effective potential and then proceed. First plot the effective potential that we were taking earlier. First plot the effective potential and then proceed. V effective equals to this your V R plus L square by a 2m R square. Everybody do it. What will be, how will the curve of the V effective potential for a spring force look like?
It will be a minimum above the R axis.
Minimum?
About the R-axis.
Minimum over the R-axis. Okay. Just you can share your graph in the chat box, or you can show it to me. Online students.
So now I will show it on the camera.
Yes. No, it's not visible. Can you take a picture and send it to me?
Ma'am, just wait a second. Can you see it now?
No.
Okay, I will send it.
Hi.
I will send it on WhatsApp.
Okay. What about others? I haven't had chance to interact with the online students. Let me do it right now. Okay. Where is the Zoom here?
Ma'am, I have shared it on WhatsApp. Please check. Whether it's correct.
Okay. On WhatsApp you have shared. Yes, exactly. Correct. Absolutely correct. Oh, Ame. No. You are just drawing the 1 by k x square. I want the effective potential.
This is the effective potential, I think. I check it.
This is the effective potential.
Send just one single side. Ma'am, I have drawn just the one single
Yeah,
side.
right. This graph is
Okay.
symmetric about the y-axis, so
Yeah.
but R cannot go below 0. So only the first quadrant is the real one.
Graphically, it should also map to the. I have drawn just.
Okay. It should be only in the first quadrant.
Yeah.
Okay. What other students we have? What about others?
Then I am also plotting the graph actually. I also plot the graph. Almost
Okay.
got same as the potential that whale that we got from the harmonic oscillator,
Okay.
and we got the minimum at also minimum at some point, and likewise the first graph shown in the group, the shared in the group.
Okay,
I got the
which was shared by Shubham.
yeah,
right?
almost same graph.
Almost same. Okay. Everybody could get that.
Yes.
Okay, I am doing this right now because I did not have any chance to interact with online students. That is why I'm asking. Okay.
You have a video for that?
Okay. 3 students have plotted the graph. What about others? Online students, you can just switch on your camera. Because today is the last day I will be taking your class. Neetu is here. Neetu from PDPU, right? Yes, Neetu, you're from PDPU, right? Okay. Have you also plotted the graph? Did you get the graph? What about others? We have Ravi here, then Preeti, Prashanthi, Harsha.
Hello.
Hello.
Yeah. Hi, ma'am. I'm Sachin.
Sachin, right?
Yeah.
Okay. Just on your camera. Just switch on your camera. Yes.
Yeah. Hello, ma'am.
Have you drawn the graph? Hello.
Yes, ma'am. Hello.
Yes.
I
I can hear you.
think there's a bad connection. Hello. Yeah.
No,
Yeah.
no, I can hear you properly.
Yes,
Yeah.
ma'am. Yes, ma'am. I was just no, ma'am. I did not draw the graphs. I've been taking on the notes.
Okay.
Yes. I'll do
Shall I
them.
help you out with it?
Uh, no, ma'am. I just I wanted to go through it again and do it later. That's why I wasn't
Elsewhere.
even trying it. I had to revise the whole thing once.
Okay,
It's,
okay. You want to revise everything.
Yeah, yeah.
Okay,
It's been a while since I did central force and all, so that's it.
okay, okay.
Ma'am,
And
sorry
for
to interrupt. I
but
shared my graph on the group, ma'am.
okay, okay, okay. Let me see.
I'm not calculating potential.
Oh no, 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 no. Aviroop. No.
Yes, ma'am.
This is see what we are doing here is what you have drawn for the harmonic oscillator. Matlab, you have drawn
Yes.
for half kx square, right? This is half kx square, a
No,
parabola.
ma'am. Also took the angular momentum term also.
Angular
L square divided by
momentum
2m.
also. See. If you will include L square term, then this will shift. Let me show you.
Okay, ma'am.
Okay. V effective is
Yes.
what? Your
Uh,
spring potential, that is
kx
half
square,
kx square, correct?
Yeah. And
Okay,
plus
half kx square will be this. This will be half. I'm taking only in the this quadrant. Okay. Half kx square will be a kind of a parabola, right? If you are plotting
Yes.
that, it's
Yes.
a parabola. Then, as I told you, your L square by of 2m r square will be this.
The effective forces.
This is
Yes,
your
ma'am.
L square by of 2m r square. Okay. Now, if you want to plot the effective potential, it will be
Just have to add up the points and it will
yes,
be in
yes.
between somewhere.
It will be like this.
Ma'am, actually, I think I got like this because the values of the angular momentum and the masses have to be adjusted by a slider in the online graphing calculator. So I think there might be some error in that. I chose the wrong values. I think that's why it might be
Yeah.
coming in this way.
Yes. Matlab, I just wanted to tell you what mistake you have done here. Okay.
Yeah,
I hope it is clear now.
Yes, ma'am. Yes, ma'am.
It is clear.
Yes, ma'am. Clear.
Okay. Okay.
Thank you, ma'am.
Now, yes, you're welcome. What about others? I hope it is clear to others also. Okay. Let me give you one more problem. Okay. Hello. Any issue? Somebody was asking earlier. Sorry, I interrupted.
Yes, I understood.
Sorry, I cannot hear you properly. Sri Lakshmi, right? Just write your question in the chat box. I will see. Let me just see the chat box. Okay. Write your question in the chat box. Okay. For others, what you can do is here I took an attractive potential, that is your minus k by r. Okay. Earlier when we plotted V effective, I took an attractive potential. What if I take a repulsive potential k by r? Now plot that. Hello.
Yes.
I hope you got my question. I'm saying earlier we have taken potential as minus k by r, right?
Yes.
Now take the potential as k by r, repulsive potential. Now plot the effective potential graph.
In that case, right?
Yeah.
Am I clear? I think my question is clear.
Yes, ma'am, but there would be no bound orbits in that case, right?
There will be no bound orbits. Exactly. There will be no bound orbits. In the earlier case that we plotted for V r equals to half k r square, we know there are bound orbits.
Yes, ma'am.
Okay. Whereas, however, for this repulsive potential, there will be no bound orbits. Absolutely correct. But I just want you to plot it for me. Effective potential.
Yes.
Everybody do that. You can share here on the WhatsApp, okay? Okay, somebody has already done. Yes, correct. But it will be much better if you plot your this L square by 2m term also and your K by R term also. So I know you have plotted the resultant.
So
Anyways, this is correct.
in writing the formula, I have included L square over 2m in.
I know. This is correct. Whatever the graph is correct. I'm telling you that is correct. Anybody else?
Simply that is this plus sign. So negative quadrants that you were like.
I hope everybody is plotting. All of you try. Okay. One more person is plotted. Yes, it is correct. However, what I wanted you all to, the way I wanted you all to plot was first plot L square by 2mr square. Okay. Then plot K by R. Here the slope will be. Then you plot the effective potential. It will be the effective potential. Everybody got it right. I'm absolutely happy about it. But this is how this will be L square by of 2mr square. This will be K by R at this as it is 1 by R. So slope will be relaxed compared to this one. And this is the result. Yes. Ravi. All of you have done that?
Yes.
Okay. Now let me give you one more. Okay. Take VR as K by R square. Take VR as K by R square. Now see what is the difference. Okay, one more person is right.
Yes.
As you can see, this VR is containing 1 by r square. Your other term, that is L square by 2m r square, that is also 1 by r square.
Yes.
Okay. If your K becomes this, क्या होगा? K अगर minus L square by 2m हो गया, what will happen?
The potential will be 0.
Potential will be 0. Exactly. Straight line हो जाएगा, पूरा straight line.
Yeah.
Okay. Absolutely correct. Other than that, what if your K is less than this factor by of L square by of 2m, or K is greater than L square by of 2m? Then
Like you are talking about minus L square by 2m or plus L square by 2m?
minus L square by 2m. What?
Like, so in that case it is to K less than minus L square by 2m and K greater than minus L square by 2m, right?
Okay, you can take that. It will be,
Or
you can share.
ma'am, actually I'm not thinking.
You have? Hello?
Yes, ma'am, like actually I'm not in the meeting.
It should not be. Sorry, I cannot hear you properly.
Actually, ma'am, I'm not in the Zoom meeting. That's why I can't
Okay.
share.
Okay, you cannot share. Okay.
But for like K less than minus L square by 2m, the potential would be negative, right?
Yes. Minus will be negative, yes. In the lower quadrant, yes. I hope everybody is trying.
And it seems that all this does is shift the effective force away from the origin.
Away or towards?
Depending upon which way we change the parameters,
Okay.
if we keep the actually, since this is a symmetric case, we can choose any parameter to be anything.
See, your L square will always be positive, correct?
Yes.
Your M will also be positive.
And the only thing will be that 1 by r square will be scaled down by some value.
Yes, exactly. Yes, this is what it will happen. This is how it will happen. What it will be happen? What? Okay, for when your K is equals to L square by 2m, then minus, or you can say this, what will be happening? It is 0 potential.
Yes.
Okay, otherwise for L square by 2m, plot is this. It will shift this.
Yes.
Okay.
For negative, it will be third quadrant, right?
Other quadrant.
Yes.
Okay. I think that is all for today. Differential equation of orbit. You can go through the derivation. It is given in many of the books. So all the properties I have tried to cover. conservative, angular momentum conservation. Then how does the effective force looks like? How does the effective potential looks like for different potentials? Then this is the differential equation of the orbit. One thing I would like to point out here is, if we go by the conventional method, that is, if I know my FR in terms of R and R dots, sorry, R and R dot, that is your R dot dot. Let me come back here. Okay, this is your FR. If I use this method and then find out what R as a function of time, theta as a function of time, we can do that. That is not very difficult. This is your R as a function of time. This will give you theta as a function of time. Okay. However, if you know R as a function of time, theta as a function of time, what does this mean? What does this mean? You know the generalized coordinates. This means you know the full configuration, right?
Yes.
This is what generalized coordinate definition is. If you know the generalized coordinate, then you know the full configuration of the system. However, technically it is very difficult to find out R and theta as a function of time. That is not a simple approach. So what we do is, instead of using this approach of finding out R and theta, we find as a function of time. What do? We instead find out theta, or you can say we instead find out theta, or you can say R as a function of theta. This is what we do. Okay, this gives you a simpler way. This is a better way to find out the full configuration. A lot of mathematics is involved. What do? You take U, which is 1 by R. Then you use this equation, plug in the values of du by d theta, then d2u by d theta square, and then find out this R theta. Okay, or you can say U theta, whatever. U and R are connected as U equals to 1 by R. So this is how we'll be getting this differential equation of orbit. And this differential equation is very important. This directly gives you the dependence. This gives you force, which will give you the dependence. Whether the force is inverse square, whether your force is 1 by r to the power 5, 1 by r square, and so on. Okay, I had prepared for few problems for you all to try. I have already shared my slides, day 1, day 2, and day 3, all slides for the classical mechanics. Under the classical mechanics folder, you can access it from there, and then you can try these examples.